Hello and welcome to all of you who are joining this webinar today on marine heat waves. We will leave a few seconds, maybe a minute or so, just to let people enter the virtual room. So please just bear with us a few moments before we get started today. Welcome to those of you coming in, entering the virtual room. We're just waiting a few moments for the attendees to enter. I see the numbers going up, so we'll just wait half a minute or so, maybe a minute before we begin today's webinar. I think it's hard to tell with a virtual room, but I think the room is filled up, so we can begin. Again, a very warm welcome and ciao from us here in Bologna in Italy. Welcome to today's webinar on marine heat waves in the Mediterranean Sea, hosted by the CMCC, which is the Euro-Mediterranean Centre on Climate Change, based here in Italy. My name's Ronan McAdam. I'm a junior scientist here at the CMCC. And I'll have the great pleasure today to introduce my colleague Giulia Bonino, who will be the speaker today. First of all, I will give a bit of background on what we do here at the CMCC, the context of the work we do. Certainly for those who are new here, first time at the webinars. So the CMCC is really a global scientific institution which focuses on the study and modeling of climate change and its effect on society. And our mission, of course, is to investigate the climate system, to model it, but also to go beyond the physical climate system and study the interactions with society and mitigation policies and driving adaptation, for example. So we aim in all disciplines, not just, as you'll see, Giulia today talking about oceanography, but in many disciplines related to climate science, we try to provide a quantitative analysis for our future planet and society. And we do that within the framework of 3 research institutes, which make up the CMCC's infrastructure, let's say. So we're split into these institutes. We have the Institute for Earth System Predictions, the Institute for Climate Resilience, and the European Institute on Economics and the Environment. So as I've said, multidisciplinarity is a key word here. And within each institute, there is great collaboration, and between each institute as well. So we try and tackle everything from the modeling of the physical and the biogeochemical processes happening on our planet to the resilience actually of societies and impacts on policy and economics as well. And alongside that, we are very proud to say we have one of the most powerful computational facilities in Europe, and certainly the most in Italy, which is completely dedicated to climate change research. So we have this supercomputing center based at the new CMCC headquarters in Lecce, which allows all of this research to be done. And indeed, we are spread throughout Italy. We have many beautiful locations in which we're based, from the north to the south, the middle, and even the island of Sardinia, which allows us to network across the country as well, as you will see, because we have many members and partners with which we interact, many universities which we, for example, share teaching and PhD courses with, and other research institutions with whom we collaborate. So that's the CMCC. Now we move on with the show. So a few rules for today, let's say. Your audio and video are deactivated by default. And if you want to ask a question, please go in the Q&A section. Okay, so there's no chat, but there should be a Q&A button where you can enter your questions during the talk. And at the end, Giulia will address them. So please put them in there. And now I suppose it's time to get on with the show, and it's my great pleasure to introduce my colleague of quite a few years now, Giulia Bonino, who is a physical oceanographer. She obtained her PhD from the University of Ca' Foscari in a joint program with the CMCC. and that was on ocean modeling and upwelling systems in the ocean. And that research experience led her to spending some time at Georgia Tech in the States. And after that, she moved on to postdoc here at the CMCC, where she focused on model development, particularly of the Nemo Ocean model, continuing work on upwelling and climate variability in general and atmospheric forcing of the ocean. And a major achievement was the designing and the winning, let's say, of a ESA fellowship, so a fellowship with the European Space Agency, which, as I say, was designed by Giulia and was designed to study with various satellite products the marine heat waves occurring in the Mediterranean Sea, which is a lot of what Giulia will present today. And that 2-year project has allowed her to become an expert on extremes in the Mediterranean, and has led to her being cited by the media in the previous summers due to the very intense marine heat waves which have happened, which we will hear about today. So today, Giulia, while I let you share your screen and I stop mine, I think we're going to hear about the definition and the detection of marine heat waves, forecasting them, how good we are at forecasting them, and their physical drivers as well. So Giulia, finally it's time to pass the microphone to you.
Okay, I'm going to share the screen. Can you see it?
Yes, very clear.
Okay.
Make sure it's full screen.
Yeah, I'm going to put in the share. Okay.
There we go.
There we go. Okay. Okay. Thank you, Ronan, for the presentation, and thank you all to being here today. Today, I will try to disentangle some of the challenges related to the marine heat wave in the Mediterranean Sea. Okay, but before going on the marine heat waves, I want just to show you how is the actual situation of the temperature of the sea surface temperature. Here on the left, indeed, I'm showing the global average sea surface temperature anomaly. And as expected, we can see that is keeping rising during the last 20 years. And the trend is basically kind of 0.015 degrees Celsius per year. But the most impressive thing is that if we zoom it and we go to our basin, so the Mediterranean Sea, we can see from this picture that are from the Copernicus Marine Service that the Mediterranean Sea has accumulated like 2 degrees Celsius of warming, and especially in the Adriatic Sea, in the Eastern Sea, and in the Tyrrhenian Sea. And if we look to the average of this SST temperature anomaly, we can see that it's keeping rising as well as the global average, but is rising like with a double trend, which means that is rising with a number of 0.034 degrees Celsius per year. For this reason, the Mediterranean Sea has been studied as a hotspot for climate change. Okay. But I think what the data are saying, you can feel it, and you felt it on your skin during those last summers. And in particular, during this summer. Here, I'm showing, for example, the temperature anomaly during the 20th of July of this year. And we can see that the temperature reaches anomalies of 6 degrees Celsius. This was a particular day. Let's see, it was a marine heat waves. So if we were trying to refreshing ourselves in the sea, actually we were refreshing in a sea that was kind of really warm. Of course, these days leads to a lot of impact. For example, they lead to a mass mortality of benthic and not benthic communities. Here, for example, we are looking to the bleaching of corals. It triggers tornado and storm over the, for example, the Ligurian Sea. And these days, of course, has a several impact on the economics of the fishing and on tourism. So these days are our enemy, and and to fight those enemies, we have to define it in order to study them and to mitigate them. And here it comes the first challenge. This is the definition of those events. So now I will come back to the definition in a bit. I want just to add that I'm gonna show you the results for the definition. I wanna touch the driver of the marine heat waves since they are under debate. And also we are gonna touch the challenges of predict these events. All these challenges are touched and reviewed in this manuscript that has been accepted like 2 days ago from Dharmaraki et al. 2024, where me and Ronan are co-authors. So regarding the definition, in 2016, Obday defined for the first time the marine heat waves, because before we were treating it like SST extreme. So the definition says that a marine heat wave is a prolonged, discrete, anomalously warm water event in a particular location. Look into the picture here below. If we look to the black line, that is a time series of the sea surface temperature, anomalously mean that the temperature has to be warmer than a threshold, that is the green line, in a 30-year baseline climatology, the blue line. It has to be discrete, meaning that it has to have a well-defined start date and end date, and it has to be persistent for at least 5 days. Already from the definition, we can see that we have 4 words that give us like a lot of freedom in order to define a marine heat wave. For example, the first choice to be made is to select where to assess the marine heat waves. The marine heat waves can be assessed in the surface, and this is useful for assessing this extreme in an observational dataset, since the data are mostly available at the surface, or they can be assessed as subsurface. And this is usually used for assess this extreme in the models. And sometimes the subsurface marine heat waves are more realistic for ecosystem impact. The second choice to be made is related to the threshold. The threshold could be specific, meaning that we are gonna evaluate the anomaly above an absolute temperature. And this is useful when we know if we are gonna study a specific location, or if we are gonna study some specific species that we know their temperature of tolerance. Or the threshold could be relative. And is usually a quantile-based threshold, meaning, for example, the 90 or the 90 percentile of the temperature. And this method, this approach, is useful when we want to study based on global scale events, or we want to compare different locations of different marine ecosystems. The third choice to be made is relative to the climatology to be used to calculate the anomaly. The climatology could be fixed, meaning that it refers to a specific period independently to the year that we are studying. While moving baseline means that the period is shifting in time dependently on the year that we are studying. For example, if I want to evaluate the marine heat waves in 2003, I'm going to take the climatology of the 20 or 30 year before this year, that year. Here, for example, I put the result from Rosselló et al. 2023. They calculated the marine heat waves days in the period of 2000-2021 using a fixed baseline. During the period was this one, fixed or using a moving baseline. We can notice that using a fixed baseline, the number of days double it, the number of days using a moving baseline. That's because using a fixed baseline, we are basically not detrending our signal to the long-term long-term warming, while using a moving baseline, we are detrending the signal. So the first approach is useful to study the trends and the marine ecosystem that are slow to adapt, while the second approach is useful to study the interannual variability of the marine heat waves and to study ecosystems with fast ability to adapt. The last choice to be made is related to the spatial criteria. The classic, let's say, definition is evaluating marine heat wave in the pixel, which means that our analysis is function of the resolution of our data set. And this is useful to study marine heat wave in a given location. While in the last years is taking place the concept of event-based, meaning that we are putting together all the pixel-based analysis in order to connect these marine heat waves in space and time, in order to have a macroscopic event or a basin scale event. And this is useful if you want to study basin scale event or an ensemble of this. So I think that the message from those slides is that the definition basically depends on your objective of your study. The objective of our study in the framework of the ESA project that Ronan told you before, called FeverC, was to detect and to document marine heatwave extreme events in a consistent framework. So since we were working with ESA, we used the satellite data, so the ESA CCI SST, and so we assessed the marine heat waves at a surface. Then our objective was to document in a consistent framework over the Mediterranean Sea. So we use our relative threshold, the 90 percentile, and we use a moving baseline climatology in order to detrend our signal. And we also did a step forward, and we use a connected component analysis in order to pass from a pixel-based dataset to an event-based dataset. We published this dataset last year in Earth System Science Data. Here is the title. But now I want to just to show you some results from this analysis. Here is the result for the pixel-based detection. And I'm showing the marine heat waves characteristics. So here we have the number of events per year, the mean duration, the mean intensity, and the max intensity. We can notice that in the Mediterranean Sea, we have more or less from 1 to 3 events per year. And the strongest and the longest marine heat waves are located in the Gulf of Lion, in the Adriatic Sea, and in the Aegean Sea. So that, as I said, we pass from a pixel-based to an event-based dataset. So we put together all the pixels that were connected in time and space. Here I'm showing what this video is showing how a macro events look like. So each color defines a macro event, and our algorithm detected this red, like just one event. There was the famous event of summer marine heat wave in 2003, and we can see that it was quite big, quite long. It was kind of basin scale. We found 68,000 macro events in those regions. So I will come back to this data set in a bit, because we use this to unravel the second challenge, that is the driver. Of course, the driver depends on the process involved. They can be local and they can be also large-scale processes. From the literature, we know that the surface heat fluxes contribute to the observed surface warming during the onset. That means before the peak of a marine heat wave. If you remember the time series that I showed before, you have the marine heat wave start, then has a peak and then decline. So during the onset, 92% of the events detected in the Mediterranean Sea, the heat flux contributes. And we can, these results is from the work of Greek colleague, where we are co-author as well. And from this plot, the A plot, we can see the number of events and the relative importance of the heat fluxes related to the tendency of the SST anomaly. And we can see that for the red, let's say the onset, the value are always positive. And if we look to the major, if the heat flux here are the major contributor of the onset of a marine heat wave, we can notice that the 42% of the events are driving by the heat fluxes. Then in the literature are also taking place a lot of work regarding the large-scale precursors of the marine heat waves. Here, for example, I'm showing results from Simon et al. 2023, where they shows that the specific marine heat wave events here are related to a positive anomaly of Z500 above the Mediterranean Sea. But then we ask ourselves, what's the link between these two? What's the link between the large-scale precursors and the local-scale precursor? And the other question is, what is causing those large-scale anomalies? We decide to investigate better this, to try to answer to those questions. And as I said, we started from our data set of macro events in the Mediterranean, and we selected the biggest events. Once we selected the biggest events, we clustered them in order to have cluster of events that share characteristics. Here are the cluster that we obtain, and we can see that the cluster represents the spatial distribution of these macro events. So we have three clusters: the cluster for the Western Mediterranean with 26 events, the cluster for the Central Mediterranean with 12 events, and the cluster for the Eastern Mediterranean with 14 events. Once we got our events, we start to look at the precursors. So how we did it? We calculate composite of Z500 anomaly 5 days prior the marine heat wave peak. The peak indicates when the marine heat wave experienced the first growth in terms of area. So basically, we sum all the pixels for each day that were experienced marine heat waves, and we look at the time series, and we pick the 5 days prior the peak. Here we have the results. On the top panels, we have the marine heat wave intensity of our cluster, so Western Mediterranean, Central Mediterranean, and Eastern Mediterranean. And here we have the composite for the Z500 anomaly. And we can see that we have a really high signal of positive anomaly of Z500, suggesting the anticyclonic condition over the Mediterranean during the onset of the marine heat waves. So once we, let's say, found this this anticyclonic condition, we ask ourselves about the precursor. So which is causing this anomaly? What is causing this anomaly? So inspired by atmospheric heat wave works, we looked at two processes. We looked to subtropical ridges that are an extension of subtropical belt beyond its zonal mean latitude. So basically, they are meanders of westerly flow, which are redirected on the Mediterranean Sea. And we look also to blocks that are similar to the subtropical ridges, but the anomaly are closed and are trapped here, are not like an extension of the anomaly. To evaluate them, we calculate index of both of them, and we calculate the composite of the 5 days prior to the peak. And here we have the result for the subtropical ridges on the top and for the blocks on the bottom. What's the message here is that if we look to the blocks, for example, we don't have any really high value, and neither they are significant. So we can say that the blocking is not a drivers of a marine heat waves here. In contrast, if we look to our index of subtropical ridges, we can notice that we have a really high frequency during the onset of our extremes, and they are significant. So we found a precursors of the atmospheric condition during the marine heat waves. But how we can link this large-scale process to the warming? And this is the mechanism that we propose. So the subtropical ridges leads to an anomaly of Z500 over the Mediterranean, meaning that we are going to have a really stable condition. This stable condition leads to a weaker wind over the Mediterranean. Weaker wind means less evaporation, which means higher latent heat anomaly, which means that the ocean is losing less heat. Then to verify it, we calculated the relative importance of the latent heat over the sea surface tendency. And we can notice that we have like the latent heat contributed for more than 80% to the SST tendency, so that we can conclude that the subtropical ridges over the Mediterranean Sea determines surface marine heat waves. And this is the title of the paper that we want to submit in the future, like in a week or so. Okay, so then we can pass to the third challenge. That is the prediction and the projections. Of course, the marine heat waves are rare by definition, so it's hard to predict them. And the prediction, of course, depends on the horizon forecast, on the forecast horizon. For the short-term horizon, we assess the skill of the Mediterranean forecasting of the CMCC Mediterranean forecasting system in forecasting the Mediterranean Sea heat wave of summer 2022. Here in those plots, we have the satellite observation on the left, and on the right, we have the forecast. And the contours highlight the area where marine heat wave was happening. What we can say is that the spatial patterns of both the anomaly and the marine heat waves are really well forecasted. And if we look much in detail, for example, for the Ligurian Sea and the Gulf of Taranto, we can see that the forecast of the SST that are in blue, in dark blue, were highly accurate. And indeed, the root mean square error is 0.12 degrees for the Ligurian Sea and 0.08 degrees Celsius for the Gulf of Taranto. We also did another work on the short-term horizon forecast. This was a work that we published this year. We applied machine learning method in order to predict sea surface temperature and marine heat waves. We applied those models in this 16 area all over the Mediterranean Sea. And this work was part of the ESA project as well. And the model that we apply were the long short-term memory model, the convolutional neural network model, and the random forest model. The model were multi-step models. That means that they predict 7 time steps of SST into the future. And our benchmark was the Mediterranean forecasting systems. Here I'm showing the results for 3 regions, region 4, region 11, and region 15, for all the model that we apply, and also for the dynamical model, the MHWs here in blue, for the SST in terms of root mean square error, that means the lower the better. And we are showing also results for the marine heat waves in order of prediction scale. That means the higher the better. What we can say is that, of course, with the forecast lead that are here in the x-axis, the forecast is decreasing. The powerful of the forecast is decreasing, but the SST and the marine heat wave prediction are comparable, or sometimes better with respect to MHWs, up to 5 days of prediction. And another thing that we can notice is that for the marine heat waves, the long short-term memory outperform the CNN and the random forest. I want to stress that this was a proof of concept of work, and a lot of other work and study are needed to apply machine learning method to predict sea surface temperature and marine heat waves. Going a step forward on the forecast horizon, Ronan published this work last year, where he was assessing the skill of the seasonal forecast system of the CMCC in forecasting the marine heat waves. In those plots, we can see the observation here on the left and the forecast here on the right for the number of days of marine heat wave in surface top panel and subsurface bottom panel. The first thing that we can notice is that the marine heat waves that manifest at the surface do not always leave a signal on the subsurface. And another thing that we can notice that we kind of underestimate the number of days here in surface, and we have, even though they are in another place, we have some sort of predictability here that is evident if we look to this box plot here. So the box plot are the average of the ensemble mean of the forecast for the subsurface and for the surface here, in comparison to the observation in green and to the reanalysis in blue. What we can notice is that the correlation between the subsurface forecast and the reanalysis is higher than the surface forecast and the observation. So basically the point is that the subsurface extreme indicator are easier to predict than the surface indicator. Okay, then what about projection? I cannot do a skill assessment of the projection, of course, but I can just show you what's next, what's the future of those events. And here I'm showing the work from Rossello et al. 2023, where they assess marine heatwave days, top panel, and anomaly, marine heatwaves anomaly, in the satellite and in the scenarios, using a fixed baseline climatology and a moving baseline climatology. We can see that the results are pretty different. As regard the fixed baseline, we have a saturation of days for marine heatwave with the worst scenario. And the anomaly is reach something like 5 degrees Celsius. Instead, if we look to the moving baseline, we have a sort of plateau or constant values, either for the marine heatwaves days and for the mean anomaly. So basically, we come back another time of the first challenge, the definition. Okay, so I try to disentangle a bit the challenges during this presentation, these 3 challenges, and I try to explain how the CMCC and the work that we have been done try to answer and to give contribution to those challenges. But what is really clear is that these challenges leave place to a really high number of works and also new challenges. And of course, as CMCC, we are already working on them. Indeed, for example, in the framework of the definition and the projection challenges, we are part of OPSI for Clean European project that started 8 months ago, where the objective is to deliver an improved framework of essential ocean variable in supporting the regional and global climate assessment and projection. In this project, we are actively involved in the generation of new ocean indicator for marine heat waves in the Mediterranean Sea, so for EXIM. And we are also leading the work package where we are using this indicator that there will be developing during the project in improving the Earth system model. Moreover, we are also facing new challenges. The new challenge is like to assess the impact of the extreme on marine ecosystem. I didn't mention this yet because I'm facing this challenge since 1 year when I joined the biogeochemical modeling group at CMCC, led by Momme Butension. Regarding this new challenge, it is one, I think is one of the most pressing one. We are doing work on it. For example, for FutureMARES, we rank the seagrass habitats according to the marine heatwave exposure. So basically what we did for each grid point, each pixel where we know that there is a seagrass habitat, we calculated an integral of the marine heatwave category over time, which is basically another way to see the marine heatwaves. It's calculate the severity of the marine heatwaves. It's a number from 1 to 5, more or less. And then we calculate for each pixel the mean and the trend of this index. Then we calculate the quartile. If one of these habitats is in the upper quartile in terms of both the mean and the trends, we said that they are the most vulnerable seagrass habitats, and so on. Finally, we are working on this challenge also in another project, a European project, ACTNOW, that we are actively involved. This project aims to advance the understanding and the forecasting of the impact of climate change on marine ecosystem. And in this project, we are in charge of develop technology, method, and models to quantify and forecast the impacts on marine ecosystem. And in particular, together with the University of Bologna, we are coupling the in-house biogeochemical model BFM with an unstructured ocean model SHIFEM in order to assess the impact of the extreme on the seagrass. That's all on my side. Thank you very much.
Thank you very much, Giulia. Excellent. We've left plenty of time, 20 minutes for questions. You can leave the slides up on the screen in case we want to refer back to them.
Mm-hmm.
So let's begin then with the questions. So the first comes from Adrian. I think there's two questions in one here. So initially, Adrian wanted to know what the lead times are for your forecasts. And I think that question came through when you were on the short-term forecasting section. And then,
yes.
And then they say also, did you also compare the forecast to the default of a persistence forecast? So as a benchmark.
Okay, so the lead time for the forecast, I think it was referring to this one.
I think so, yeah.
It's with, I think, lead 4, if I'm not wrong. And for the question of Adrian about the machine learning approach, we compare with a linear regression model, and it was better than that.
Okay, great. We have some more questions. To the rest of you, don't be shy. Please get your questions in. So we now move on to the question from Panos regarding the heat wave of 2022. What was the forecast time horizon? A day, a week, a month? And was this marine heat wave related to a well-predicted subtropical ridge?
So, okay. So for we are always speaking about this slide, right?
I believe so, yeah. So
yeah, the time horizon regarding this was the Mediterranean forecast system that has like 9 days of forecast, I think. And here I'm showing for the leading time of 4 days. Was this related to the well-predicted subtropical region over the Mediterranean Sea? Yeah, actually, we are verifying this with the driver, with our driver analysis, because the heat wave of 2022 belonged to the cluster of the Western Mediterranean. So I think that this heat wave was related to the subtropical regions.
Okay, and I suppose the sub-question within that, whether the subtropical ridge was well predicted or not. Not sure there's an answer to that yet.
Me neither.
Something for the future then. We have a next question here from Clinton. So a distinction was made between blocking highs and subtropical ridges, presumably the North African anticyclones extending towards the Mediterranean in the summer. Could it be the reason that the blocking highs normally happen in winter season of the Mediterranean and hence do not influence the SST?
That could be a reason, yeah. Yeah, that's really a good point. But yes, we should maybe try to verify this. But in principle, I think that could be a reason that if usually the block happens in winter, probably this could be a reason why we cannot say that we don't have any signal of the blocking for in relation of the sea surface temperature during the summer.
But just to follow on from that, the clustering analysis you did there of the marine heatwave events, was that done on all events throughout the calendar year, or was it just the summer?
No, we did for the publication 2023, we did for all the events. Then for the analysis that we are made for the drivers, we are doing I redid it just considering the events during the extended summer.
Okay, good. We move on now. Plenty more questions coming through. Let's try our best to get through them. If not, well, we have 15 minutes. We should be successful. If not, don't worry. We will reply to you via email. Right, for Miriam, thank you very much for a nice presentation. A question related more to the attribution of marine heat waves. Which definition do you think is more appropriate? And was SST still a relevant driver to consider?
So what I think is more appropriate definition for marine heat waves is there is a comment on Nature posted by Amaya et al. 2023, where he was saying that probably the best way to analyze marine heat waves is to analyze it using a moving baseline climatology, and then study either the marine heat waves, like using the baseline, the climatology, and also consider the long-term warming. So when you are speaking about marine heat wave, you should consider both, not just one of these two definition. And what was the second question?
About SST still being the most relevant
okay,
to consider.
So that was the things that I wanted to show, like in the first slides. Yeah, so we are considering SST because it's what we had from data, actually, that we have this coverage of the satellite data that is giving us SST. But of course, sometimes the SST is not so relevant for marine ecosystem. For example, indeed, also Ronan in his work is used ocean heat content in the 40 integrated in 40 meters. So yeah, I don't think that SST is always relevant, at least for the marine ecosystems.
Okay, now we have a question from Mary. Thank you again. Did you also consider using mean sea level pressure for marine heat waves, or did you only consider Z500?
No, we also did composite of sea level pressure during the 5 days prior to the peak of the marine heat waves, but the signal was not so clear as the signal in Z500, not for all the clusters, at least.
Okay, I think we have Miriam again. Why we assess climate effects just on the surface and subsurface seas? I don't know if that should be why we do it on the surface and not the subsurface, but anyway, you can talk about the differences maybe of the effects of both.
Yeah, in our case, we used the surface just because we were using satellite data, so this was why we used the SST instead of the subsurface sea. Of course, if we had more data of the subsurface, it would be great to do the same work for the subsurface sea, because of course it's more relevant for the marine ecosystems.
And now from Gerard, regarding the subtropical ridges, were there any particular Atlantic SST precursors?
Okay, I didn't.
Did you consider any occurrences in the Atlantic? Any variables there? Anything noticed?
No. I was thinking about the No, we didn't check the Atlantic condition. I was just thinking about a work from Simon et al. 2023, the one that I show you, that she was saying that, but I think it's not related to this question actually, that she was saying that probably the marine heat waves in the Mediterranean, it could be linked to the summer North Atlantic oscillation, but we didn't look at the SST in the Atlantic.
Okay, that's still to be done. I think in terms of the Atlantic, you did show figures which showed, significant differences in atmospheric circulation, the subtropical ridges over the Atlantic. But the SST itself in the Atlantic, not studied. Okay. We move on from Bayumi. Many thanks for the very nice presentations. For the moving baseline climatology, do you suggest to remove a linear or non-linear trend?
Actually, the thing is that if you use a moving baseline climatology, you are kind of removing the signal itself without removing before. So yes, anyway, I'm suggesting even if you are using a fixed baseline, I would suggest to remove the trend, because there are two different things. We are thinking about long-term warming and marine heat waves. That's are two different things, as stated Amaya et al. 2003 in their Nature comments.
Okay, very good. We're nearly coming to the end of the questions, but it's not too late for anyone else who wants to write something in the Q&A. So here we have Ashwini. If understood right, the prediction of marine heat waves defined by surface water temperature was linked to atmospheric heat waves. So I guess that's the first question. Were the ones we studied, were they linked to atmospheric heat waves?
No.
Second, was there any attempt at predicting the marine heat wave from linking it to forecasting of water temperature from the past in the same area or adjacent areas? So I imagine that means using the SST as a predictor.
Oh, okay. So for the first part of the question, no, we were linking the anomaly of the surface water temperature to the subtropical ridges. We were not comparing or looking at the concurrence of atmospheric heat waves and the surface water or marine heat wave. Sometimes, so I think this is next steps, and I know that a lot of people is looking at it, and they are in some way related, but I don't know if they are really concurrent. For the second question. Okay, so an attempt of linking forecasting from the past. So with the machine learning method that I show you, in order to predict marine heat wave, we use a predictor, the SST itself. So yes, but we use the SST to predict SST in a particular point. We used the past SST in the same place. We didn't took the SST in another place. Actually, I tried a bit, but it wasn't so successful. So I just took the SST in the same place where I making the prediction.
Okay, then I think we're at the last question, as far as I can see, from Marani. If and how are the marine heatwave forecasts being used by ecosystem services within the Mediterranean region?
As far as I know, not yet. But we are planning also in the CMCC website also to put information on the marine heat waves forecast, so that it could be available for everyone to have prediction, to forecast of marine heat wave in the Mediterranean, but we are working on it to be online soon.
Yes, that's a very important big picture question that I think many in the scientific community are trying to address. And it was an excellent question. I think all the questions were excellent, those technical and those big picture. And I see no more questions in the chat. So I think, Giulia, we can wrap it up here. We can thank everyone again for attending this CMCC webinar today and
Thank
for
you.
the many useful questions. Am I right in saying people can contact you, Giulia, by email if they have some follow-up, some comments? Absolutely welcome. And of course, Giulia, I thank you again for a very clear and jam-packed presentation. And thank you for this webinar. Thank you, everyone, and goodbye for now.
Thank you.
Ciao, ciao.
Ciao, ciao.